Hey, so we're about to start our last chapter, chapter 8, and it's all about sequences and series. And how we can rewrite functions as a series and integrate or differentiate with the series. So the first thing you're probably asking is, what the hell is a series? Well, a sequence is pretty easy. A sequence is just a set of numbers, right? But a series is the sum of those numbers. And then when we write it as a function, we're writing it as the sum of polynomials. So for example, hard to believe, e to the x is the series. So that symbol is capital sigma, right, from Greek letters. It means sum of I equals 0 to n of x to the n over n factorial. And it's hard to believe that this e to the x curve is actually a sum of polynomials, right? And so there's a couple of weird things in here. Anybody notice something weird? Oh, first of all, sorry. I should have, this is I, sorry. My index is I, right? First one, second one. Oh, actually, one more time, sorry. I'm going to do it as n. Sorry. So don't erase what you had before. X to the n over n factorial. That's the one I want, sorry. So my index is n, and I'm starting at 0. What's telling you I'm starting at 0?
N equals 0 at the bottom of the sigma?
Exactly. So I can see that I'm starting at x to the 0 over 0 factorial. And then plus, and what's telling me the plus?
The sigma?
The sigma, exactly. The sigma is telling me the plus, right? And then I've got x to the 1 over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. What's telling me the dot, dot, dot?
Infinity?
Yeah, the infinity, right. So it's saying that this representation of polynomials is going to be the function e to the x in the long run. What else is still weird here for any of us?
Factorial?
The factorial piece. But some of us might not even realize it says factorial. So this n factorial is n times n minus 1 times n minus 2 times dot, 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 all the way down to 3 times 2 times 1 times 0 factorial, and 0 factorial is 1. So you can see, just having that particular piece, I can start rewriting this as 1 over 1, right? Because x to the 0 is 1. But by the way, we're going to let x to the 0 be 1 in all of chapter 8. It's usually not allowed. Right? 0 to the 0, in the earlier in our lives, mathematical lives, we said you can't do it, right? But now we're going to say 0 to the 0 is 1. So x to the 0 now can be 1. And so I have what? Plus x squared over 2 plus x cubed over 6 plus dot, dot, dot. So I'm writing out those factorials now, right? 3 factorial, right, is 3 times 2 times 1 times 0 factorial is 6. So pretty crazy, but you can see here, I'm confused about it. If I'm confused about it, what do I do first? First, I write it out as general as I can, write things out as general as you can, and then try and simplify them, right? So that's the first thing you have to do with all these sequences and series, is start writing them out. And you're going to use lots of paper, right? And you got a couple things to remember now, right? X to the 0 can be 1. 0 factorial is 1. What is a factorial? And et cetera, et cetera. Now, the interesting thing here is me showing you that this is kind of true. So let me do that. So let me go to Desmos. Now it's going to feel like we're in a completely different class right now, right? But by the end, we're going to connect everything. By the time I get to section 8.6, 8.7, 8.5, 8.6, 8.7, I'm going to connect everything we've done all the way back to the beginning of integration, okay? So it'll be weird for the next couple of classes. You'll be like, what the hell's going on? But at least that's what I was like. So I've got my y equals e to the x function in red, and I want to compare that to the sum of those things I got, right? And I, I know it's a little bit easier for you to look at your screen here, but we're comparing it to 1 and plus x squared over 2 plus x cubed over 6. By the time I get there, I should see the connection, right? So I'm going to start just with the 1. So y equals 1. And it's not a great connection. It does connect at a single point to the function, right? It's a good representation of the function when x is what? This line, y equals 1, is a perfect connection of the function when the x value is what?
0.
Exactly. E to the 0 is 1. I mean, it's trivial, right? But we're going to go further. So I'm going to take that same function, and now I'm going to add my plus x. Is that correct? Is that my next term? Now look at this thing. It connects a little bit more, a little bit past the origin, right? It connects to that red. It is a tangent line, by the way, right? Calc 1. But it looks like it covers more of the red than a singleton point, right? And so what if I add my next piece here? Plus, was it plus x squared over 2? Oh, look at how that blue is now taking over more of the red function, right? And so this is what we're saying. We're saying, okay, I've got a function e to the x. Okay, not difficult, I know, but we're going to have some very difficult functions that we can't do anything with. But if we could turn them into polynomials and let the polynomials represent the portion of the piece that we're interested in, now all of a sudden we've got a very powerful thing. We take a function that's impossible to work with and turn it into polynomials, the easiest functions to work with, right? What was my last one? X cubed over 6. Is that correct? X cubed over 6. And look how close this blue piece is covering that curve of the red function now. Now it looks like it's almost working from -1 to 1, right? Can you see the curve from -1 to 1? And I'll just cut off some of that. From -1 is less than x, which is less than 1. Look at how good that blue curve is representing that red piece of the e to the x. I mean, not perfect at -1, right? But I mean, minus 0.75 to 0.75, it's identical. And that's the idea, right? In Calc 1, we were trying to make lines represent curves, right? So we had tangent lines all over every place, and you could see the curvature from just the tangent lines. And now we're saying, well, we have this really difficult curve. Let's get a representation of it from polynomials. So kind of cool. So there's lots of processes we're going to be doing in Chapter 8 to figure out how to make these series, right? How, different types of series, and they're called power series and Maclaurin series and Taylor series, and then the other piece is how close is the representation, right? So you could see here that it looks like I've got a pretty good representation from -1 to 1. Is that making sense? Is anything I'm saying there making sense? From -1 to 1 here, the blue curve is a pretty good representation of the red curve. It's on top of it, right?
Yes, that makes sense. You could integrate. If you didn't know how to integrate e to the x, you could integrate 1 plus x plus all that and find almost the same thing.
Exactly the same thing. And, depending on, what we do at the beginning is we start to see, well, how good are these series to represent, right? So right now I'm thinking -1 to 1, but could it go further? It turns out that this one represents from -infinity to infinity. And so that's our first start. So that's going to be really weird. And then we go into, well, how do you test if these series converge or not? Kind of like our improper integrals. So we come up with all these tests to say, well, will this one converge or will it not converge, right? If it converges, good, let's keep moving forward. We got something that we can work with. If it doesn't converge, well, it's dead in the water, right? We're gonna try and work on something else. And then the final piece is, how do you come up with a series? And then how do you integrate? So kind of our first thing, 8182, is a review of sequences and series. Right? How do you represent them? Do they converge? How do you find the convergence, etc.? 8.3 to 8.4, I think it's 8.3 and 8.4, are just a bunch of convergence tests for series. And there's I don't know, 8 or 9 of them. Please look at them on Paul's notes. He's got a nice listing of them, and I'll post that on our page too, of what you should try first, what you should try second. I don't have time to test you on 8 or 9 of them. I test you on, I think, 2 or 3 of them, and I'll tell you which ones I test on, right? And then 8.5 is my ratio test, sorry. And then 8.6 is the power series. This might not be quite perfect, but it's the idea. Power series representation, and then 8.7 is Maclaurin series representation.
Is it the same kind of convergence as with the improper integrals?
Exactly. And then there's a comparison test, right? There's an integral test. So the integral test is identical. I turn my series into a function, and then integrate. And if the integral converges, the series converges. So lots of connections here. Just strange notation. That's what I'm worried about the most here. And I could be off by the numbers here, but it's basically 4 major points here. A review, which I'm not testing you on. All of the tests, and I will test you on a few, and I'll tell you which ones. Creating a power series, and then integrating with the power series. Creating a Maclaurin series, and then integrating with the Maclaurin series. So creation and then integration. Right? So review, convergence, creation, integration. 4 pieces here, right? So again, we're just talking in general what we're doing here with chapter 8, but let's look at the big issue. So this is, we're basically doing this for one particular problem that the book showed us very early when we started integrating. Probably was there for Simpson's rule, or maybe even the original Riemann sums in Calc 1, and that is this function y equals e to the x squared. This function cannot be integrated. Cannot be integrated. So what we're going to do, and remember this is 8.7 I'm talking about right now. Okay, we're going to turn this into a series and then integrate it. And we already know that e to the x is represented. Well, I didn't show you how I came up with it, or I didn't come up with it, of course. N equals 0 to infinity of x to the n over n factorial. And we already saw that e to the 0, oh, and what was that? 1 plus x squared over 2 plus x cubed over 6 plus dot, dot, dot. You can already see if I plug in 0, right, I get 1 plus 0 squared over 2 plus 0 cubed over 6 plus dot, dot, dot. Obviously, e to the 0 is 1. And remember how I was showing you when I had that first piece in, I got a good representation of e to the 0. And then if I put in the two pieces of the function, I got a better representation, a little wider representation, etc. So, but what we're going to do is turn this series into e to the x squared. So what do you think I should do? What's your gut say here? My gut says, I'm hungry. What's your gut say, mathematical gut say here?
You could express that as x to the n squared over n factorial.
Exactly. You can just take the x and put in what I have now, which is x squared, and I still have it to the nth power. So now my series is n equals 0 to infinity of x to the 2n over n factorial. And there's in this chapter, there's things that easy that we will overthink because we're humans. There are things that are that simple that all you have to do is, wherever the x was, replace, right? And so now this particular series can be written as, well, so remember what I said, write it out like you're doing baby steps first here. X to the 2 times 0 over 0 factorial plus x to the 2 times 1 over 1 factorial plus x to the 2 times 2 over 2 factorial. And at that point, I can almost stop using the formula. Right, I see x to the 0 plus x to the 2 upstairs. So I see evens upstairs, right? And then downstairs, I'm going to see the 0 half of the exponent factorial. So 1 factorial. So 2 factorial. So 3 factorial, etc. Sorry, over 6. And so now I got a pretty good representation of e to the x squared. Again, this particular representation is only working really from -1 to 1. We're going to talk about how big that interval of convergence is, or radius of convergence. Right now my radius goes from -1 to 1, right? So radius of 1. But now I can finally integrate. And it's very easy. And that's what we're working on in Chapter 8. How we can have some function that none of our processes work for integration. Turn it into a series, right? So we have a function that we can't integrate. None of our steps work. Integration by parts doesn't work, etc. Turn it into a series. Find out if that series converges or not. If it doesn't converge, stop wasting your time. You're working on something that can't be done, right? How good is the convergence? What is the ratio? What is the radius of convergence or the interval of convergence? And then finally, integrate, right? And you'll see on my test, I give something that you can do by parts, and then something that I would have you do with Simpson's rule, and then something I would have you do with this particular series called the Maclaurin series, and see how much better the Maclaurin series is than Simpson's rule. And again, if you think about, some of us are going to be engineers, mechanical engineers, civil engineers. We're going to be building machinery or engines or buildings. And am I going to be able to cut one piece of steel exactly the length I need? No. So I'm going to have to approximate, and I have all these safety things inside of this to make sure I approximate correctly. And then am I going to measure? No. I'm going to have the computer do it, and do everything with these super precise approximation, computer driven integration things, right? So pretty cool, pretty exciting, but very different, right? Remember how I told you I thought pre-cal was very eclectic? You'd be doing something, and then all of a sudden you're doing something completely different. This is a big chunk of that. I kind of feel that same way in Calc 2, right? We did integration, fine. Then all of a sudden we're rotating things around an axis. We're doing volumes, and then we're looking at families of curves, and now we're looking at sequences of series. So a little bit hodgepodge in my opinion, but still beautiful. Questions for me? Nothing? Anybody a little freaked out, like never seen this stuff before? Or I appreciate my past students for not saying anything like, no, I've never seen it before. I haven't taught pre-cal in about 2 years, so I would never have seen any of you for pre-cal, but I saw, let's see, 1, 2, 3, 4, 5, 6 of you for Calc 1, so right, we definitely saw it there. Okay, let's start 8.1 sequences. So a sequence is simply a list of numbers, right? I guess A sub n, right? So I'll do the Fibonacci sequence: 1, 1, 2, 3, 5, 8. Right? Anybody know what comes next?
13.
Yeah, 13. So I'm just adding the next two numbers together, right? Next would be 21, right? And so I can see A sub n as A sub n minus 1 plus A sub n minus 2. Oh, that's it. Sorry. So So this guy is the sequence, right? And this one is called the nth term. How do I get the very next term, right? And this particular one is a recursive sequence. It depends upon the previous terms. We don't always have to have one like that, right? So for example, this is just one of the examples in the book. Is this clear to everyone? So like a sub 3 should be what? A sub 2 plus a sub 1, right? So a sub 3 should be 1 plus 1. Right? Is that making sense? Is that subscript connecting to everyone? And the subscripts are weird here, right? These little subscripts are weird, but it's just telling you which element you want to take, right? So here's a sequence. For example, 1/2, 2/3, 3/4, 4/5, etc. You can really see, you can play the easy game, what comes next. Obviously, 5/6 and then 6/7. It's usually pretty easy for us as human beings to pick up patterns like this. What's my nth term here, though? What do you think? Well, let's assume I start at the first term, right? And then my second term is the second. I mean, it's kind of silly when I say it, right? But n is 1 to start, and then n is 2, and then n is 3. N is a counter or an index, right? So this should be n over n plus 1, right? So if I kind of start writing these out, a sub 1 is 1 over 1 plus 1. Okay, that's 1 over 2. Oh, it worked. Check. A sub 2 is 2 over 2 plus 1. You see what I mean by writing these out without really thinking at all? I'm just plugging in and writing it out and see what happens. So I get 2 over 3. Oh, it worked. Right? So finding an nth term or taking an nth term and turning it into a sequence is one of the basic things you should do. And if you read all the examples in 8.1 and write them out, and that's what I'm expecting you to do in the next day, 8.1 and 8.2, right? You should get a good grasp on this. Now, if you've done this stuff before, and this 8.1, 8.2 is what I do in pre-calc class, okay? So if you've done this stuff before, then you should be fine as we move on to 8.3. But if you haven't done it before, and no one would tell me if they did it or didn't do it yet, you want to practice it this way, right? Just be really, really clear about what's going on. There's a couple of weird ones, I guess. Like if I alternate between positives and negatives. So let's just look at that one real quick. So here's my sequence. Is this okay with everybody? Is everybody comfortable with what's going on here? Can anybody talk to me? Is it are you going to give me the Monday excuse, or is it you're just pissed off about the midterm, or? So this is a particular sequence that shows up a lot. And so I want to generate a positive one when my integers are odd, and a negative one when my integers are even. Okay. Right. So if I think about this, n is 1, n is 3, n is 5, right, I'm getting positives from the odd numbers. And so I can clear that up, right? So, but typically I'm going to use this thing called 2n plus 1. Does that work for me here? Give me 1 second. So negative 1 to the 2n plus 1. Let me see if I can write this out. I'm just confusing myself for a second. So what's that? Minus 1 to the 2 times 1 plus 1. Okay, that's negative. Sorry. And then
is it necessary to have a 2 in front of the n plus 1?
Yeah. I'm just confusing myself. Give me 1 second. Sorry. Oh, sorry. It's exactly right. I don't need the 2. Thank you, David. And so now when I plug in an odd and I add 1, I get an even, right? So this is this is now minus 1. Sorry, that's supposed to be a curly bracket. Minus 1 to the 1 plus 1. And then what? Minus 1 to the 2 plus 1. Yeah, and that's the idea. So there's lots of ways to do this. They'll come up a couple of times where you've got to have a different little sequence like this. Here, this is another interesting one. So this is, right, positive, negative, positive, negative. Another one would be odd numbers. And this is where I was confusing myself. This is a sub 1 equals 2n plus 1 minus 1. Right, when n is 1, I get 2, right? Let me not shortcut it. Let me write it out, right? I get 2 times 1 minus 1, 2 times 2 minus 1, 2 times 3 minus 1, etc. And you'll see that that gives me, right, it gives me exactly the 1, the 3, the 5. So odd number sequence, plus minus number sequence, right? All kinds of little things in there. Okay, I just need about a 5-10 minute break. So it's 9:15. Let's come back at 9:30. Be right back. So what's your gut on this one? Does this one converge? In green?
No.
Yeah, no, this is unbounded. So we're going back to limits here. We're going back to Calc 1 with limits here. Does this particular piece converge? Right? When does something have a limit? When it's hey, will you shut that door, please? When doesn't have a limit? When it doesn't have a limit is easier, right? Oscillating, unbounded, goes to infinity or minus infinity, or the other one doesn't really happen. Different from the left and different from the right. That one's really not going to happen for us. So we're kind of going back to limits here. What about this one? Does this one converge?
No.
Right, and that's the oscillator, right? On, off, just constantly going back and forth between these two numbers. So we're looking for these things to get closer to and closer to a number in order for them to have a limit, right? And so we can write this a couple of ways. So we're looking at the limit of sequences. And it's going to tie into, this is going to tie into, you know how I was saying, well, it looks like it works from -1 to 1, right? So this is going to tie into that a little bit later. So we say a sequence a sub n has the limit L, and that's got to be a real number, of course, if the limit as n goes to infinity of a sub n equals L. So very much like our old limits from so we're looking at these limits of these sequences. Do they have limits, right? Or are they unbounded, or are they oscillating? And it's going to tell us something, okay? It's going to tell us something about the convergence a little bit later on, but we're just trying to review that we know how to find these limits, right? So example, if a sub n equals n over n plus 1, right, find the limit. And that one's really easy, right? The limit is as n goes to infinity of n over n plus 1. What could we do here? What are you seeing?
Longer division things?
I could do long division. Nice. I could do long division, right? So this would be the limit as n goes to infinity of, what is it? 1, help me, n plus 1 into n is 1, and then minus 1. Yeah, minus 1 over n plus 1, correct. And then, of course, we know that that second limit is 0, right? Could we have done something else there?
Did you apply L'Hopital's rule?
Exactly. So the limit as n goes to infinity of n over n plus 1 is the same as the limit as n goes to infinity of n prime over n plus 1 prime, right? And there's a little hop there, right? I got infinity over infinity. So that's the limit as n goes to infinity of 1 over 1, which of course is 1. So all of your little Calc 1 limit skills are going to come back into play in this particular section. An interesting one is if a sub n is minus 1 to the n over n. That's an interesting one. And of course we could, so I'm a little confused about it, I can start writing it out, right? And so what do I see here? I've got minus. So when n is odd, I'm going to get a negative, right? So minus 1 over 1 plus, so comma, plus 1 over 2, comma, minus 1 over 3, right? You with me there? And I can see in the long run, this limit is going to go to 0, right? So this is oscillating, but it right? So it starts at minus 1 and then minus 1/2 and then, right? So it's oscillating, but you can still see it's getting to that it's going to go to 0, right? And these are kind of fun to graph. These are nice to graph on Desmos or your calculator, right? I don't really think you need it on your test, but you certainly can look it up, how to graph a sequence on your calculator. But I like to do it on Desmos, so let me do that. So I'm just graphing the sequence on Desmos. And it usually will just send me to a general link here. And then I like to do this and then manipulate. So here's n is 10, right? And I'm writing it, instead of in terms of n, I'm writing it in terms of x. And then I'm plotting those points. So for example, if I change n to 23, you can see it's writing out more of my particular sequence. So what did I have? I had something like x over n plus 1, right? So I'm writing that as x over x plus 1. And you can see I'm getting to that line closer and closer to the line 1, right? As I write out that sequence more and more, it gets so dense that it just looks like a line anymore. But you can see that I've got a horizontal asymptote, so that's telling me I have a limit. So those are kind of fun to look at when you're practicing in 8.1. You certainly can look at that. You know, look at it on Desmos. Try it on your TIs. So there's another way to tell if something has a limit, to tell if a particular sequence has a limit. If I can just show it's always increasing or always decreasing, and there's a bound, then I know there's a limit. So I think this is our last little piece today that we're doing. Yep. Every bounded monotonic sequence is convergent, so it has a limit. That's all I need to be convergent. Does it have a limit, right? So every bounded monotonic sequence is convergent. What does convergent mean? There's a limit, right? So I'm assuming that this is kind of obvious here. Monotonic meaning always increasing or always decreasing, right? A sub n is greater than a sub n plus 1, tells me, right, my sequence is decreasing. Obviously, if they're equal, like if the sequence is 3, 3, 3, 3, 3, 3, I don't care about this, right? So less than equal is not that interesting. Greater than equal, not that interesting. If they're equal, I don't care about it. I can just find the limit right away, right? So if a sub n is less than a sub n plus 1, right? Now my terms are getting bigger, right? The sequence is increasing. And bounded, right? The bounded piece should be exactly that visual I gave you here, right? That bounded piece is exactly that I get a horizontal asymptote. And remember, I can have a horizontal asymptote being crossed, right? It can cross in the short run, but in the long run, it should not be crossing. Does that make sense? Remember that all that pre-cal stuff about horizontal asymptote, long run behavior, short run behavior, all of that stuff. So obviously, if it's increasing, I need it to be bounded above, right? If it's increasing, it must be bounded above. Bounded above, right? So what do we have? We had a sub n is n times n over n plus 1, right? And we looked at that particular thing. It's getting bigger and bigger and bigger, but towards 1, we already know it has a limit. So definitely increasing and definitely bounded above, right? Increasing, bounded above. All right, so what the hell is the point of this? Well, what's the point of anything, right? Sometimes I can't find the limit, but I can show that these two things happen. So if I can't find the limit, but can show that it's increasing and show that it's bounded above, then I already know that the limit exists, right?
Could you explain that last part one more time?
Yes. Is that Josh? Yes, Josh.
Yeah, you said if it was bounded or above, you should know if it's.
Yeah, exactly. Exactly. So if I have a bound above, meaning it never, you know. So if I'm saying that this is definitely bounded by 1, right? So n over n plus 1 is never bigger than 1, right? Do we agree with that? N is never bigger than n plus 1. 0 is never bigger than 1, right? So we agree with all of that. So it's bounded above. Turns out that this is the limit, and this one's easy to find the limit, right? But it's also so this is showing me bounded above, right? It's never above 1, and I can tell from the graph. How can I show that it's increasing, right? I can show that n over n plus 1 is less than n plus 1 over n plus 1 plus 1. I've increased my integer, right, from the first n to the next n, right? And so what do I get there? I should be able to show that n over n plus 1 is less than n plus 1 over n plus 2. And yes, it's trivial. I cross multiply, I get n times n plus 2. Is less than n plus 1 squared, right? What do I get? I get n squared plus 2n is less than n squared plus 2n plus 1, and I get 0 is less than 1 again. So this is showing me increasing. So there's nice ways to show something's increasing other than this process. So a sub n is n over n plus 1. I can turn it into a f of x, which is x over x plus 1, right? And then I can do a derivative. So what's my derivative here? We've got x plus 1 minus x all over x plus 1 squared. I got 1 over x plus 1 squared. What kind of numbers come out of that? Always positive. If my derivative is positive, the function must be increasing. So all kinds of these little tricks from pre-cal or calc 1 to show that something's increasing, something is bounded, that type of thing. All right, so you've got some. I don't have a WebAssign homework up there for 8. I'm going to put it up there, so I'm going to do that today. Okay. I will try and limit it, the homework in Chapter 8, to 1 or 2, less than 5 questions, and just one major theme. Find the limit, show it's bounded. Find the nth term, something nice and simple like that. And if you want more problems, I certainly don't mind problems in 8.1. I really want you reading the textbook. Do the examples in the book, in the lecture. I think that's a better way to go. Caleb just came in. Good morning, Caleb. You should have gotten your test emailed, graded and emailed back to you. And you should be able to see your grades on Blackboard.
Yeah, I see the grade.
And you should be able to see my solutions I posted on Blackboard too.
Yep.
So, I saw this. Yeah, so just want I want everyone to go over their exam with my solutions and then get back to me and ask me questions. Okay?
Yep.
So today we're stopping here because I have about 11 students that want to meet quickly one-on-one. You're going to be put into breakout rooms at random, and I'm going to choose them in order. So I have about 11 students. I'm going to create 19 rooms. There's 19 students. You're going to be put into the rooms randomly. Okay, I'm not picking the order. I'm sorry about that. So if you're number 19 and you want to go get a cup of coffee, feel free to. Okay. And then, so just so you know, and I don't expect to be more than five minutes or so with each student. So, but if 19 of you fill the rooms, that is an hour, right? So, but just be patient with me. I'm sorry if you get the bad pick. It is still class time, so I think it's pretty fair. Certainly, you could get some breakfast or put on some music until I get there. Okay.
Robert, can you scroll up to the decreasing part before we go?
Yeah. So I just showed the increasing, right? So bounded I showed I knew the limit was 1 because we did it. So I just showed that every term was going to be less than 1. And then I did the increasing. And so the key there is I started with n, like 5, and then went to n is 6, right? So it compared an n to an n plus 1.
What is a monotonic sequence? Like
bounded and an increasing, bounded above and increasing, or bounded below and decreasing.
Okay.
Yeah, monotonic meaning always taking a step, whether it's up or down, right? Never hitting like a flat plateau, right? Where you're just at the same level every time.
Right.
So constantly decreasing or constantly increasing. And if I'm constantly increasing, of course, I could have no limit. So I need it to be bounded above if it's increasing in order to get a limit. And it seems kind of random, but there's a couple of examples in there. I think most of the time, the ones that we're going to be looking at, you're going to be able to find the limit. But this is just an alternative if you can't find the limit. But of course we can. Then if you just show, so it's one of the things they want you to be able to show. Show it's always increasing. Easy way, get the derivative. Show it's always positive. Show it's always decreasing. Get the derivative. Show it's always negative, right? Show it's bounded above. I mean, pick your gut instinct and show that every term is below that, right? Like the sequence we had -1 to 1 to -1. Is that bounded above? This is bounded above by 2, right? There's no number in that sequence that's bigger than 2, so it's bounded above. But is it always getting bigger? No, it's doing this, so no limit. Okay, we ready for breakout rooms? Anything you want to tell me? Now you don't have to join the breakout room. Okay, so if I create 19 breakout rooms and only 10 of you join, someone still could be number 19. But so don't just be okay with it. And then so you don't have to join your breakout room. You can meet with me privately after any class, scheduled or in office hour. And you'd probably want to do that if you're after you go over your midterm, you don't understand anything, right? If there's something on there that you don't understand.